All right. Okay, so 3.1, looking at probability, we're going to have some vocab just talking about some of the basics, and then we're going to look at the 3 different types of probability. Okay, so probability is the foundation of inferential statistics, which is what we're going to primarily be looking at the remainder of the semester or the school year. Okay, so a probability experiment is an action or trial through which specific results are obtained. Okay. So as we talk about this, our example is going to be rolling a die. Okay, so rolling a 6-sided die. The sample space is the set of all possible outcomes. Of a probability experiment. Okay. So if we roll a die, what are all of our possible outcomes?
1 through 6.
Like what numbers can we get?
1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, 6. So we use a set brace, like the squiggly bracket, and we just list everything out. Okay. So if the sample that we're looking at was statistics students, the sample space would be each of your names. Okay. So that's what a sample space is. The event is what we're wanting to find the probability of. But for the actual definition, it's a subset. Of the sample space. Okay, so say the event we're looking at is rolling an even number. Okay, so rolling an even number is our event. Okay. So if that's our event, what are our possible outcomes? What could we get? What would make that true? 2, 4, 6. So there's our subset. Okay. The outcome is the result of a single trial. Okay. So our example, we roll a die, and let's say we roll a 2. Okay. That set of that outcome would just be the set braces around the 2. Okay. All right. So there's the main things about a probability experiment. Then we can look at different ways of representing them. Okay, so the first one we're going to look at is a tree diagram. Okay, so a tree diagram gives a visual representation of the outcomes of a probability experiment by using branches. Okay. So it's a way to organize your list for your sample space. Okay. So for example, a survey consists of asking people for their blood types. including whether they are Rh positive or Rh negative. Determine the number of outcomes and identify the sample space. So we have 4 different blood types. So we have O, A, B, AB. And then from each of those, we're going to create branches. So we could have O positive or O negative. A positive, A negative. Oops. What positive? Negative, positive, negative. Okay. So then our sample space is listing out each of those. Okay. So each of those branches, so we would have O positive, O negative, A positive, A negative, B positive, B negative, AB positive, AB negative. So how many possible outcomes are there? 8. So they're great because they're visual, but the more things you're looking at, the more tedious they get, okay? And they're kind of a pain. So we very rarely will use tree diagrams when we're representing sample spaces, okay? But they are a nice way to organize it. Okay, simple event is an event that consists of one single outcome. Okay. So one single outcome. So looking at examples of this, determine the number of outcomes for each event, decide whether or not it's simple. So for quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. How many are you drawing? How many are you picking up? One. Okay, so there's one outcome. Which means yes, it is simple. Okay, you roll a 6-sided die. Event B is rolling at least a 4. So how many numbers are there that are at least a 4? 3. You would have 4, 5, and 6, which means there are 3 outcomes. So is it simple? No. It's not simple because it doesn't have one outcome. There's 3 possible. Okay. Okay, questions with that page? All right. So in some cases, an event can concur in so many different ways, it's not practical to write out all the outcomes. So not making that tree diagram. So what we'll use instead is the fundamental counting principle. And this says if one event can occur in m ways, and a second event can occur in n ways, then the number of ways the 2 events can occur in sequence is m times n. You're just multiplying them together. So if you have 3 different things occurring, it'd be n times O. Okay, you just keep multiplying them together. Okay, so if you think back to the blood one we just did, we had 4 different blood types, and then we had the positive, negative. 4 times 2 is 8, which is how we had our 8 outcomes. It's the same idea, okay? So if you're purchasing a new car, you have 2 different manufacturers, or sorry, 3 different manufacturers. You have 2 car sizes, and you have 4 colors. Okay, how many different ways can you select one manufacturer, 1 car size, and 1 color? You're just multiplying those all together. 3 times 2 times 4, which is what? So 24 ways you can pick a car. Okay. And then we'll eventually get to the point where we say, okay, what's the probability that this person picked a Ford Compact that's red? Well, that'd be 1 out of the 24. Okay, because there was 24 possible options. Okay. Access code for a car security system consists of 4 digits. Each digit can be any number from 0 through 9. How many access codes are possible if each digit can be used only once and not repeated? Okay, 0 through 9, how many digits is that? 10. So there's 10 numbers possible. Okay. If we have 4 digits, I'm going to put 4 spaces. Okay, each digit can be used only once and not repeated. So how many options do you have for the first number? 10. Okay, but then the number can't be repeated. So then how many options do you have for the second number? 9. The third number? And the fourth number? And then multiply them all together. So how many different passcodes could you have for access codes? 5,040. Okay. What if each digit can be repeated? What would they all be? 10. So what's 10 to the 4th power? 10,000. Number of zeros will match the exponent. Okay, so 10 to the 5th would have 5 zeros. Okay. All right, each digit can be repeated, but the first digit cannot be a 0 or a 1. So how many options do you have for the first digit? 8. And then the next 3 digits, they can be repeated. So what would it be? 10. Okay, what's 10 cubed? 1,000 times 8? 8,000 ways. And that's the fundamental counting principle. Are we okay with that? Cool. All right. Types of probability. We have 3 different types. Okay. Main thing, make sure you know, round off rule is going to be 3 decimal places when necessary. Usually on your homework, if it wants more than 3, it'll tell you. Okay. And we'll talk about when you would do more than 3. It may not be today. We might talk about it tomorrow. Okay. So first one we have is classical or theoretical. I don't care which name you use. This is the one you know, okay? So this is used when each outcome in a sample space is equally likely to occur. Equally likely is the key part there. Okay, so rolling a die, getting any of those numbers, you have an equal chance of getting 1 through 6. Okay. Our formula for that, the probability of E, of event E, equals the number of outcomes in event E divided by the total number of outcomes in the sample space. So the one you know. Okay. How many of you know what a deck of cards looks like? If you don't, now's the time to start figuring out what a deck of cards looks like. Okay. And I play some solitaire. I don't know. Download an app. Do something. Talk to your grandparents. Play some cards. Okay. Standard deck of playing cards. You have 4 suits. You have 13 different cards. Okay. 2 through ace. There's your picture for it. Okay. What's 4 times 13? How many total cards are there? 52. All right, 52 total cards. So event A, find the probability of selecting a 9 of clubs. How many 9s of clubs are there? 1. So the probability of event A is 1 over, how many total cards were there? 52. And then divide. So what's 1 divided by 52 rounded to 3 decimal places? But 3 decimal places is going to make it? Yep, you're good. Okay, selecting a heart. So there's 4 suits. How many did I say were down? 13. So the probability of event B would be 13 over the 52, which would be what? 1/4 or 0.25. And the probability of selecting an ace, 4 out of 52, or 1/13, which is what as a decimal? 0.077. Okay. The deck of cards are not going away. This picture either needs to be your best friend or start memorizing it. Okay. All right. Empirical probability, this is going to be your relative frequency. Okay. F divided by N. Okay. It's based on observations. Okay. So usually you're given like a table or a chart. Okay. So F divided by N, and it's based on observations. Okay. Flip to the back real quick. I'm gonna go over a couple key things and then we'll finish these up tomorrow. Okay, subjective probability. It's subjective, okay? So these results from intuition, how about from? Educated guesses. Or estimates. This is the weatherman. There's a 50% chance it's going to rain today. Okay. It's a guess. There's no way to surely know. Okay. The other couple things that you need for your homework, the range of probabilities rule. All your probabilities have to be between 0 and 1. Okay. They can't be negative, and they can't be greater than 1 or greater than 100%. Okay. And the last thing that you're going to need for your homework is this complement. Okay. So this is the set of all outcomes E in a sample space that are not included. Okay. The notation for it is called E prime, which is simply the probability of E to the first power. That's what it looks like. Which would just be 1 minus the probability of E. Okay. So this example real quick. Okay, I'm gonna keep you guys on for this last example. Okay, so using the frequency distribution, which means we're finding empirical probability, find the probability of randomly selecting a social networking site user who's not 25 to 35 years old. The easiest way to do this is to find the probability of it actually happening. So 23 to 35. So looking at our table, we know there's 312 that actually are 23 to 35. So this is going to be 312 over our total frequency, which this is the same thing as our N. Okay. So 975. And if we calculate that, we get 0.32. So then the probability of not 23 to 35 equals 1 minus that 0.32, which would be 0.68. Okay, so you're just subtracting. Okay, let me stop recording that.